So in this changing dimensions, applying that scale factor, let's start with our rectangles that we have here. Every dimension of rectangle A has been multiplied by 2 to form rectangle B. So in other words, they're saying apply a scale factor of 2. Let's just write that right here. Scale factor of 2. So if we apply a scale factor of 2, the figure should get bigger. It should get 2 times bigger. Okay, so at least let's start with the dimensions and see what it does to the dimensions. So what would be the new dimensions? If rectangle A has dimensions 2 centimeters by 6 centimeters, what would rectangle B's dimensions be? Devin?
4 centimeters by 12.
Okay, 4 centimeters by 12 centimeters, he says. Everybody agree? Any disagreement here? We want to change his mind? Okay. Well, then it says, what is the ratio of corresponding sides? You just did that for today. Remember, you set up relationships of corresponding sides. And what did we say the relationship of corresponding sides should be between similar figures? What should be true about the ratio of corresponding sides between similar figures? What should be true about the ratio of corresponding sides between similar figures? I'm not looking for a number answer here. Just trying to find one. What does this say right here? Ratio of corresponding sides, ratio of corresponding sides, ratio of corresponding sides. They should be what? Not similar. They should be equal. They should be exactly the same. They should be equal. So the ratio of corresponding sides, in this rectangle should be equal. Well, would that be true? If we put this 4 over here, 4 centimeters by 12 centimeters, and we set up ratio of the corresponding sides, would we get equal ratios? So let's try it. We could compare. Oh, by the way, just a little, make sure you keep this in mind. When we are comparing, when we apply a scale factor, we always compare the new figure to the old figure. New to old, not old to new. Our old figure compared to the new figure. Okay, so our new figure, excuse me, I just said that backwards. New figure compared to the old figure, okay? So we're going to say ratio of corresponding sides. This one has a height, width, whatever you want to call it, of 4. The other one, its corresponding one is 2. So what does that equal? 4 over 2? 2. And the other, the length, or we could say the base, they sometimes call that, 12, the new, over the original, 6, and 12 over 6 is 2. So the ratio of corresponding sides is? They're equal, yeah. And it is what? It's 2, right? We just got 2. Oh, well, 2 is the same as the scale factor, isn't it? So does that make sense that if we multiply, if we apply a scale factor of 2, shouldn't the sides now, when you divide them out, shouldn't you get a ratio of corresponding sides of the same thing, of 2, right? Okay, let's explore then what happens, because a rectangle is a 2-dimensional figure, so we can't work with volume with it, but we can work with perimeter and area. So let's complete this table. How do we find perimeter? Add all the sides together. It's the distance around, isn't it? Okay, so for rectangle A, what are we going to add together? For rectangle A, what are we going to add together? 2 plus 2 plus 6 plus, okay, it's 4-sided, right? What does that equal? 16. And what are those? What would the label be on that? Centimeters, because when you add centimeters to more centimeters, you still have centimeters in the end, don't you? Okay. How about rectangle B? What's its perimeter? Well, we got to add what?
4 plus 4.
4 plus 4
Plus 12.
plus 12 plus 12, and what's that equal? 32. Okay. And those are centimeters. Okay. Okay, well, let's do the area now. do we find the area of a rectangle? Andrew?
Length times width.
Length times width. So for rectangle A, we're gonna take
6 times 2.
6 times 2, and we're gonna get
12
12. And that's what label for that one?
centimeters cubed.
6 centimeters times 12 centimeters. Centimeters times centimeters is? Centimeters squared. We have 2 factors of centimeters. Centimeters times centimeters. Centimeters squared. All students always struggle with this, being able to label perimeter, area, and volume correctly. Okay, how about rectangle B? How are we going to find its area?
4 times 12.
4 times 12. And that is?
48 centimeters
48.
squared.
And that would be centimeters squared. You're right. Okay. Okay, so we have our table filled out like they've asked us to do. Now they are asking in number 4, what is the ratio of the perimeters? So which one starts the ratio out? What's upstairs? 16. The new or the old? The new. The new. So maybe we should put ratios. We want new over old. Okay? New over old. So we want the 32 over what was it before we applied the scale factor? 16. And what does 32 over 16 divide out to? 2. Okay? So there's no label on this. We're comparing their perimeters. We're saying, what's the ratio of the perimeters? Well, the ratio of the perimeters is 2. Well, tell me then, how is that related then to the ratio of the corresponding sides? How is that related to the ratio of the corresponding sides? Compare them. They are what? They're equal. They're the same, aren't they? So the ratio of perimeters will be the same. So ratio of perimeters is the same as the ratio of corresponding sides. And tell me, what else did we say about the ratio of corresponding sides? It's really the same as what? The ratio of the corresponding sides is also the same as what?
Scale factor.
The scale factor. So we can really think of it like this. If you apply a scale factor, the perimeter is going to change by the same amount. The perimeter should change by the same amount. If you double the side lengths, the perimeter should also double. Okay, what's the ratio of the areas? Well, new to old, so what? 48 over 12. What does that divide out to? 4. There are 4 12s in 48. So the ratio of the areas is not 2 like it was for the perimeter and the sides. It is 4. So how is that related to the ratio of the corresponding sides? It's double. Or it's self multiplied times itself, right? 2 times 2 is 4. And multiplying by 2, when 2 is the base, we could say, well, 2 times 2 could also be called 2 squared, right? So let's call it the square of, because I think that's what we're going to find out, is that the ratio of the areas is the square of the ratio of corresponding sides. So the ratio of the areas is the square of, in other words, we take the ratio of the corresponding sides times itself, and that'll tell us how many times bigger the area will get. So the area is not going to just double, it's going to What's the area gonna do? It's not gonna just double, it's going to? It's not gonna just get 2 times bigger, it's going to get 4 times bigger. Okay, let me prove that. Okay, will you verify for me, gentlemen, that the dimensions of those 2 rectangles double? The scale factor is 2?
Yes.
You're gonna verify that for me?
Yeah.
So now, we talked about that the perimeter should change by, so remember perimeter is the distance around, right? So let me start with the small one, the one that we started with. Here's my first one. Now this doesn't have exactly the dimensions that our one up there does, but it's just another example. So would you guys verify for me that you put that around for me, just kind of like wrap it around, and then here, go ahead, Jason, you do this one. I might want to go out of the way for a second. Would you wrap that one around for me and see if it goes around? If I have those correct. Yeah, so you're kind of like tucking away in the corner, but I'll help you. Okay, so Brayden, you're going to tell the class that this does represent the perimeter of the smaller rectangle. So here's the perimeter of my smaller rectangle, okay, got it? Here it is. How you doing here, Chase? Need some help? How you feeling about this? You think that's the perimeter? Okay. So Chase says that this is the perimeter of the larger rectangle. Okay, I want you to see that. If I compare these 2 perimeters, there's where the short one, the smaller one ends, and here's when I flip it over and put it and line them up again. I have, how many times can the short one fit in the long one? Twice. So by doubling, by applying a scale factor of 2, the perimeter got twice as long. Perimeter of the small one, perimeter of the new one, it got twice as long. Okay, now let's look at the area. Remember, area means how much coverage is there. So here's the small one. Here's the new one. Would only 2 of these fit on here? How many of these would fit on here? 4 of them. So the area got 4 times bigger, not just twice as big, did it? It got 4 times bigger. The scale factor, the sides got doubled. The scale factor times itself. 2 times 2 is 4. Okay, there's this problem in your homework, I believe it is today, and it has something to do about pizza. In fact, let's go find it. Because I think this is kind of an interesting one that it talks about, where is it at? Anybody see a pizza problem? We're in 19? Okay, at Pizza Palace, yeah. A pizza with a diameter of 8 inches costs $6. The restaurant manager says that a 16-inch pizza should be priced at $12 because the pizza is twice as large. So if the smaller one is $6 and the dimension got doubled, that means we now have a 16-inch pizza. And he says, well, if you're charging $6 for the smaller pizza, you should charge $12, twice the price for the larger one because it got twice as big. How do you feel about that? Seems logical? Okay. So when we're talking about twice as big, are we talking about when they say that it has a diameter of 8 inches and the other one has a diameter of 16 inches, are they saying anything about what's the perimeter of a circle called? Circumference. Are they saying anything about the circumference? Or are they talking about the coverage, like how much, area is covered? Which one are they talking about? The area that's covered because the dimension got twice as big. So then that means the pizza gets twice as big, huh? Okay, this is for real. This is an 8-inch pizza without any toppings. And this is a 16-inch pizza without any toppings. 16-inch diameter, 8-inch diameter, double the diameter. Would I only get 2 of these on here? How many? 4. Why is it 4?
Because it's like the area.
It's like the area of the rectangle, yeah. We doubled the dimension, so the area gets not 2 times bigger, but 4 times bigger. 2 times 2, doesn't it? Yeah. So again, hoping that the visuals will help you say, you know what? Even though it seems like it should just double, it doesn't get double, it gets doubled. 2 times 2, it gets 4 times bigger. Okay, let's go talk about volume now. What happens to the volume then? So we have these rectangular prisms, and we have a prism A that has dimensions 5 inches by 6 inches by 3 inches. And we want to know what would be the new dimensions of prism B if we double, so we're still in the doubling category, if we have a scale factor of 2. Let's put that here. Again, it's being doubled, so scale factor of 2. So what would the new dimensions be for rectangular prism B? Instead of 5 inches by 6 inches by 3 inches, Austin?
10 inches by 12 inches by 6 inches.
10 inches by 12 inches by 6 inches. Is that what I heard? Okay. Everybody agree? Okay. Well then, let's set up some ratios of corresponding sides. So the new side, 10 inch, corresponds with which side? The 5 inch, okay. So 10 over 5. What's that equal? 2. The next side, 12 over, it corresponds with 6, and that equals 2. And the 6 inch corresponds with the 3 inch, and that equals
2.
well, of course, the ratio of corresponding sides is 2, because why? Because we doubled it, because the scale factor is 2. So of course the ratio of corresponding sides is 2. Duh, did we have to go through all that? Probably not. What is the volume of prism A? How do we find the volume of a prism? If it's a rectangular prism, we do length times width times height. Well, that's easy enough, right? So volume for prism A, 5 times 6 times 3. 5 times 6 is?
30.
And 3/30 is?
90.
90. And the label is?
Inches cubed.
Good job. Inches cubed. Inches times inches times inches. We have 3 factors of inches. Okay, find the volume of prism B. Check me out, because you know I started the week horribly. My Monday was not so good. Maybe my Friday's not going to be either. Do I have a good answer? I do? Okay. Well then now it says, what is the ratio of those volumes? So 720 over 90. Oh, and you guys are getting your calculator. Are you kidding me? Cross all these zeros, and how many 9s are in 72? 8. Ratio of the volumes is 8. So in other words, they're saying that that prism, an original prism, would get 8 times bigger because we doubled the dimensions. So let's see if that would actually happen, okay? Okay, Andrew, did you tell me, what are the dimensions of that cube?
3 by 3 by 3.
A 3 by 3 by 3. Okay, well that would have tripled. How about those 2 cubes? Will you tell me what the dimensions of those guys are? 2 by 2 by 2. You guys, and that's a 1 by 1 by 1. So if we double the dimensions, it went from side length 1 to side length 2. And a cube, of course, all 3 dimensions are the same. Would you tell me, ladies, how many of these smaller cubes, the original cube, do you think I could fit inside that? 4? 8 more inches. Okay, guys, tell me, what do you think? You give your opinion. How many of those small ones do you think I could fit in there? 8? 8? Okay. Caitlin, what do you think? One last, because we see if anybody else wants. 8 of them. So 8 of these smaller ones would fit inside one that the side lengths got doubled, the dimensions got doubled. So 8. Well, let's talk about then how's the ratio of volumes then? That ratio of 8, how is that related to the ratio of corresponding sides, which there was 2? Or in other words, our scale factor was 2, and our ratio of volumes is 8. So let's just start this out. Ratio of volumes is a relationship can you think of between 2 and 8? Times 4.
About 4 times
4 times 2 is 8.
Cubed by itself.
Or what was that?
It's cubed by itself.
Or 2 to the 3rd power is 8?
Yeah.
Ah, I think that's probably the one we're looking for. If the scale factor is 2, and we double 3 dimensions, a length, a height, and a width, 2 times 2 times 2 is 8. Oh, so the ratio of the volumes is the cube of the ratio of corresponding sides. Or in other words, we said again, one more time, the ratio of corresponding sides is really the what? Scale factor. So we can think of it like this. Take the scale factor and cube it. Whatever the scale factor is, cube it, and that'll tell you what the volume is going to change by. How many times bigger or smaller it is going to get. Okay? So all of this was just kind of like exploring and saying, what should happen? Anybody have questions about any of those? Because now we're going to apply that to problems on the backside, like you will do in your homework. And there's no pictures, look at that. Oh dear. A rectangle has a width of 3 inches and a length of 12 inches. Every dimension of that rectangle is multiplied by 1/3, I might underline that, multiplied by 1/3 to form a similar rectangle. Because if you do it to all of them, you're just changing the ratios the same for all of them, so you're creating a similar figure. So what's our scale factor?
1/3.
1/3. So in other words, the ratio of corresponding sides should be 1/3, right? So how would the ratio of the perimeters compare to the ratio of the corresponding sides? Or in other words, how would the perimeters, let's just think of it this way, how would the perimeters compare to this scale factor? What would happen to the perimeters? The perimeter of the new one?
It would be smaller.
It would be smaller. And how much smaller?
3 times.
It would be 3 times smaller. It would be 1/3 the original perimeter, wouldn't it? So that we're going to say the perimeter of the new one is 1/3 the perimeter of the original. The original is bigger. We apply a scale factor of 1/3. So not only do the dimensions change by dividing by 3, but so does the perimeter. We would take the perimeter of the original and we would divide it by 3, and we would have the perimeter of the new, wouldn't we? And notice, we didn't even draw a picture, find all those dimensions. Do we have to? No, we use what we discovered on the front side to say, you know what, this is what should happen. How would the ratio of the areas compare to the ratio of the corresponding sides? Or in other words, we're going to say, what should happen to the areas? How's the area of the new one going to compare to the area of the original? What happens? Remember, on the front, what did we say? The ratio of the areas is the square of the ratio of the corresponding sides. Well, ratio of corresponding sides is the scale factor. The scale factor in this is,
1/3.
we're supposed to do what with that 1/3? Square it. So let's just show that. 1/3 times 1/3 is 1/9. So tell me then, The area of the new one is what?
9 times smaller.
9 times smaller, or 1/9. You could say 9 times smaller, or you could say is 1/9 the area of the original. So we got 9 times smaller, or if we compared it, we would say it is 1/9 the area of the bigger rectangle that we started with. Okay, questions at all on either of those? Okay, let's try this next one. We have a triangle. It has an area of 20 inches squared. Every dimension of the triangle is multiplied by a scale factor, and the new triangle has an area of 180 inches squared. What was the scale factor? Oh, different question this time. What was the scale factor? What did they give us? The 2 areas. So we could set up a, let's write what we're going to set up. We're going to set up a ratio of areas, because that's what we have to work with. So we have a ratio of areas we can set up. New to old. So what would go upstairs? 180 over 20. And what's that divide out to? 9. So the ratio of the areas is 9. So what was the scale factor?
3.
It was 3. Because remember, the ratio of the areas is the square of the scale factor. So what we're looking for is what squared equals 9. What squared equals 9? Well, that's 3. So we're going to say the scale factor is 3. There. Okay, so notice, we didn't worry about trying to draw this triangle and try to figure out how did they get that area of 20 inches squared, or how did they get that area of 80 inches squared. We don't really, or 180, we don't really care, because we can set up a ratio of their areas and say, we know that the ratio of the areas has to be the square of the scale factor, and that's what we were looking for. Okay, let's try this next one. We have a cylinder that has a radius of 3 centimeters and a length of 10 centimeters. Or in other words, it's 10 centimeters high. This would be laying on its side when we call it the length. Every dimension of the cylinder is multiplied by 3 to form a new cylinder. How would the ratio of the volumes compare to the ratio of the corresponding dimensions? How would the ratio of the volumes compare to the ratio of the corresponding volumes? Well, did they give us a scale factor?
Yeah.
Hallelujah. Okay, so scale factor is 3. Okay? Well then, the question was, how would the ratio of the volumes? So what's going to happen to the volume?
12 times.
Go look on the front. What happened? What did we discover about the ratio of the volumes compared to the ratio of the corresponding sides? It gets cubed.
27.
Oh, so we have to take that scale factor and we have to cube it. And 3 times 3 times 3 is 27. So we would say the volume, we'll shorten this up a little bit. The volume gets 27 times bigger. So we have this little cylinder, 3 centimeters by 10, and it's going to get every dimension. So the radius is going to get multiplied by 3, the height is going to get multiplied by 3, and wow, we have a cylinder that is 27 times bigger, not just 3 times bigger. Okay, one more of these. A cone has a volume of 36 pi centimeters cubed, and every dimension is multiplied by a scale factor to form a new cone. The new cone has a volume of 288 pi centimeters cubed. What was the scale factor? Well, the volume got bigger or smaller? Bigger, so we should have a scale factor that's what? Bigger than 1, right? Okay, so how are we gonna find it?
288 over 36.
We're gonna set up a ratio of volumes, yeah, ratio of volumes. And we're actually gonna use the pi in it and we'll cancel them out, okay? So we're gonna take the new volume. Pi is not part of the label, it's part of the number. And 36 pi is the volume of the old. And then, of course, you know that because there's no addition or subtraction happening up or down, we can go like that, yay. And then we say, how many times can you take 36 out of 288? 8 times. Okay, everybody agree? Okay, so the ratio of the volumes is 8. 8 divided by 3. Ratio of volumes is the what? The ratio of volumes is the scale factor cubed. Ratio of the volumes is the scale factor cubed. So it's 2, isn't it? 2 times 2 times 2 is 8. So this is 2. We say the scale factor is 2. The dimensions were doubled. Okay, so think you're going to be able to do this? Got it? Okay. Let's just do a little bit more practice with some similar figures and finding missing sidelines. We have triangle ACD is similar to triangle ABE, and I'm going to guess we need to solve for x in this one. So what relationships could we set up? So let's look at what we have here. We have like AE, we have ED, we have EB, we have DC. So I'm thinking maybe since we're looking for x, maybe we should start with DC. DC, what does that correspond with? EB. Okay. Well, that takes care of these two. Now I need something from triangle ACD. That's the big one, isn't it? So, can I get AC? Do I know AC? Do I know AD? Yeah. What is AD? Okay. And then what side does AD correspond with in ABE? The smaller one. AE. Yep. Okay. So AD, AE. Okay, so DC is x, length EB is 5, length AD is 8 plus 4, 12, and length AE is 8, right here, 8. So we should very easily be able to see this. X to 5 is the same as 12 to 8. We have this big rectangle that is working together with the smaller rectangle right there, okay? Go ahead, solve that. What is x equal to? You tell me.
5 centimeters.
7 and 5, 10 centimeters, 7.5 centimeters, okay? And I think I would have to agree with you. Okay. Okay, let's do one more. Triangle QRB is similar to triangle TRS. So the QRB, that's this one right here. And that is supposed to be similar to TRS. So TRS is this one. Okay. We need to solve for x. X is RS. So what side does RS correspond with in the other one? BR. RS, or RB is probably the way we should say it in the same order. RB. RS corresponds with RB, doesn't it? Okay, that should be equal to, well, we have ST, that's the other one we want to work with because we know that one, and ST corresponds with VQ. We always want to make sure we have a good relationship. We aren't just counting on the numbers they gave us in the problem. Okay, so now we can say RS is X, RB is 10. Length ST is 3 6/10. Length BQ is 6. Okay, solve for X. Yeah. But I don't think I heard any calculators. And that's 6 what? Centimeters, yeah, 6 centimeters, okay. So sometimes when our figures are connected, maybe you could say, or touching or whatever, we have to make sure that we can still have good proportional relationships, okay? Any questions at all? Nope. You want to make sure that you very carefully write down the problems you need to do. We get 3, 4, 5, 6, 7, 8, 9, 10, 11 problems. We talked about one of them already. And you have a couple of challenge problems to do, and I do not want you giving up too easily because you will regret that come Monday if you do, because there's going to be a checkup on it.